So hello everyone to a new video on job design, and now we're gonna go and do some uh, start learning about learning curves, and we're gonna do some questions on learning curves. So the main idea behind learning curves is the time required to perform a task will actually decrease with more repetitions. So you've probably seen this with your own with jobs you've done before or things you've done before, that the first time you do something it takes you a long time, then the time decreases as you repeat more and more instances of that job. And this is very important for, I guess, organizations, because they want to know, they're very interested in knowing after how many units does the worker could perform the job by a certain time. And so initially, when you first start learning to do something, the learning curve is going to be steep. So you're going to be learning at a much faster rate, and then it sort of slows down until you reach this plateau here. So it's steep at the beginning, and it's going to reach a plateau later on. So what happens if you're on the same job for many years and you already know everything that is involved in the job? What happens to your learning curve? Well, the job sometimes changes, so there's always, you cannot predict the future, and there's always going to be changes to the job, whether it's equipment changes, redesign of the equipment, redesign of the job, and so on. So at every point there's a change. We're gonna actually, so this is the curve. So when you're first learning something, you're gonna get to a plateau where your learning has been maximized, and then a change happens, so maybe an improvement. And we see this, for example, the IT system changes. So you're working on a job and the IT system that you use changes, so you end up now again trying to learn this new system, so you end up with a new learning curve activity. So this is actually called the scallop effect. So the scallop effect is basically there to tell you, even if you know your job very well, due to changes in technology and equipment, you're always gonna be seeing the learning curve effect. So the idea behind learning curves for operations management is that we wanna know how long does it take to produce some item, maybe the 10th, 20th, 30th item. So we know how long the first item takes because that's where we are. And we're interested in knowing how long would it take to make the 20th item, the 30th item, the 21st item, whatever. So we're always trying to calculate Tn based on some T1. And we could do it using formula, and we could do it using a table. Sometimes we using the formula would take a very long time, so we resort to tables. And this is especially true for the case when we're looking for the total time. So when we're looking for total time, it is faster to use tables. So right here is the main formula, which is T of n, which has to do, n is the number of units you want to predict ahead. So maybe you were interested in knowing the 18th unit. So how long does it take to produce the 18th unit? So that would be T of 18 is equal to T1 times n, and n in this case is 18 in this case, to the power of b. And b is this equation right here, the learning percentage over 100. So the learning percentage, you probably know, you probably measured before in questions, it's given to you, or you could estimate it. Now the learning percentage sometimes is going to be 90%, so the learning percentage is high, and that's gonna affect our TN, or it could be 70%, which is quite lower. So we take the learning percentage divided by 100, take the ln of this divided by ln of 2, and that's going to give us B. So let's look at this question. So I'll give you a few seconds to read the question. So here we have a manufacturer producing electric cars. We know they're giving us the time for the first car. So we know T1 is equal to 310 hours. They're telling us 85 learning percentage, 85%. How much time does it take to produce the 17th? So N in this case is 17. So now we could use the equation. It's really simple calculation. We know all the T1, we know T1, we know the percentage, we know the number of cars. So we start by calculating B. So we're going to start by calculating B right here. So B is basically ln of 0.85. So we don't put 85%, we put it as a ratio, 0.85. Or you could divide 85 by 100 and you get 0.85. So ln of 85 divided by ln of 2, we're just following the equation, it's going to give us a negative 0.23. We take that number and we plug it in into this equation. So we end up with 310 times 17 to the power of negative 0.23, and it's going to give us 159.54 hours. So we went down from 310 hours to 159 hours on the 17th unit car. So the learning curve really applies here. So let's do another question. So again, we give you a few seconds to read the question. You could always pause the video if you need more time. So the first car here is taking 330 hours, 90% learning dynamic. What is the total time it will take to produce all 12 cars? So we want to look for the total time for 12 cars. Now this is different than the previous question. The previous question, they ask us for the 17th. So how long does it take to produce the 17th car? Now it's asking us to produce all the cars up to 12. So 1 plus 2 plus 3 all the way to 12. In this case, where you want to use the table. So the table looks like this, and we have different learning percentages: 70%, 75, 85, 80, 85, and then 90. In our case, we're looking for 90 because that's the question is telling us it's a 90% learning curve behavior. Now we notice under each percentage, there's two choices. There is a unit time and a total time. So there is a unit time and a total time. Now the unit time will basically, if we want to know how long does it take to produce the 10th, 11th, 12th, 15th, and so on. The total time is basically what we're looking for in this question is all the cars. So all 12 cars, all 13 cars, all 14 cars. So this is the difference between them. So we want to go into the total time column. Now, how do we figure out what Tn? So Tn will be exactly equal to T1 times the unit time factor or the total time factor. So let's see for our question. So our question, they were telling us they were looking for the first 12 cars. How long does it take to produce the first 12 cars? And we are in the 90%, and we're looking for the total time. So we are going to get 9.374. So we just got the total time factor that we're going to use to calculate how long does it take to produce all 12 cars. So going to the back to the problem, we have T1 percentage, and we just calculated the total time factor, which is 9.374. Now, how to find T for all 12 cars? We're just going to take T1, which is given, multiply it by the factor. Very simple. We're just multiplying by the factor. So we have 330, and we got our factor to be 9.374 from the table. And we're gonna get the number of hours for all 12 cars. So we get 3,039 hours for all the 12 cars. So let's see this question. Give you a few seconds to read the question. So here we have again the electric car company, and their first car is gonna take 111 hours to make. And they're gonna start with 30 cars production run. So they're gonna start with 30 cars production run. So 30 cars run. And they're telling us 85%. Right here, learning percentage. What is the total manufacturing time for the second set of 10 cars in the run? So, so if we divide, so there's 30 cars in the run. So they're making 30 cars. So the first set is going to be 10 cars. And then 10 cars, then 10 cars. And they're asking us for these 10 cars in the middle. So this is the same thing as calculating the 20 cars and subtracting from it the first 10 cars. So we take this and we subtract from it the first car. So we're really gonna solve the problem for n equal 2, which is 20. So we wanna look at the total number of hours for the first 20 cars and subtract from it the number of total hours for the first 10 cars, and that's gonna give us the second set of 10 cars in the run. So let's go into the table and find the factors. So we know that we're looking for 10 and 20 in the table. So for 20, we go on the 85% total time, and we're gonna get 12.402, and that's for n equal 20. And then we go on to look for 10, so n equal 10, and we're gonna get 7.116. And that basically gives us the two ends we need to, the two total time factors we need for both ends. So we could go ahead and solve the problem now. So getting back to the problem, we know what N2 is, the total factor for N2 and the total factor for N1. We just got them from the table. So our Tn is going to be T1 multiplied by the difference between the total factor for 20 and the total factor for 10, and that's going to give us the answer. So we have 111 multiplied by 12.402 minus 7.116, and that's going to give us 586.75 hours to make the second set of 10 cars in the production run. So that basically concludes the questions we're doing on learning curve. And just to recap what we have done so far in job design. We talked about job design, the methods, design, environment, and then we went to talk about stopwatch studies, and we've seen how to calculate the N. Then we went on to see how we calculate the standard time. So stopwatch, standard time. Then we finally, now we did the learning curves, which includes, and we've seen when we use the equation and table. So thank you very much for watching the video, and I'll see you in the next videos.